I want to show you one of my favorite Codeforces problems. It has a really nice problem statement, very interesting setup, and a really beautiful solution, in my opinion. So let's take a look. Let's see what we're being asked for. So we have a tree on n nodes, right? So there's a root. The root might have some children. Those children might have some children, so on and so forth, right? So the whole thing, imagine a big family tree or something, but any node can have arbitrarily many children. There's one root, and then every step, we uniformly at random pick one of the nodes and delete it and all of its children and all of their children and so on, right? The whole subtree rooted of that node gets deleted. And so we keep going until we delete node 1. And the question is, what is, for this particular tree that we're given in the input, what is the average number of steps that it takes? So let's look at some examples. So obviously the simplest example is just a single node, the root. We always move it in the first step, it takes 1 turn. The next simplest example, say the root has 1 child. So 50% chance that we choose to delete the root, and then we're done. 50% chance that we choose to delete its child, and now we're back to case A, right? We have to pick the root next, so the answer is 2. So the average number of times, well, half the time we're done in 1 and half the time we're done in 2. So on average, we're done in 1.5 turns. Okay, so that's this case. Next simplest case, same thing, but the root has 2 children. So there's a 1/3 chance that we are done in 1 turn and we just remove the root. And there's a 2/3 chance that we remove either 2 or 3. It doesn't matter which one, because either way we're back to case B, which we knew was 1.5 steps. So that's 2.5 steps, right? So 1 step to remove either 2 or 3, and then on average it takes 1.5 steps from there, as we just figured out in case B. So the answer for this case, well, 1/3 of the time we're done in 1 turn, and 2/3 of the time we're done in an average of 2.5 turns. And if you just add those up, you get that it takes, on average, 2 turns for this case. Let's do one more. So now we again have 3 nodes, but instead of 3 being the child of the root, 3 is the child of 2. So, okay, so how do we do this? Well, we'll do the same thing we did before. So there's a 1/3 chance that we're done in 1 turn. There's a 1/3 chance that we remove 2, which also removes 3, right? Because when you remove a node, you remove all its children, all its descendants, in fact. So if you remove 2 and 3, then it'll always take 1 more turn to remove 1. And if we remove node 3, then we're back in case B again, where it takes an average 1.5 more turns. So to summarize, we remove node 1, we're done in 1 turn. We remove node 2, we're done in 2 turns. We remove node 3, we're done in an average of 2.5 turns. So the average number of turns for this case, 1/3 times 1 plus 1/3 times 2 plus 1/3 times 2.5, which gives us 1 5/6. Okay. So hopefully now you understand the problem and how we might solve some simple cases. How are we going to solve the full problem? So how many nodes do they want us to do? 100,000. That's a lot. So that's almost a hint, right? We have to do something pretty fast. You might hope that we could keep following the method that we've been doing in these examples, which is just consider all the nodes that you might delete on the first turn, and then think about what that leaves you with, and just recursively solve all of those, and eventually you'll get a number out of that, like we've been doing. Unfortunately, that's not going to work. There's just a huge number of possible trees that might result depending on the order that we take out the nodes. Maybe up to like n equals 10 or something that could work. But for 100,000, we need something much better, much smarter than that, much faster. Okay, so how can we actually do this? So let's flip it around a little bit. Right? So we want the average number of turns. You could think of that as the average number of nodes that ever get picked to get deleted. Right, so another way of thinking about the answer here being 1.5 is that 100% of the time you need to pick node 1. Right? No matter what the tree is, you always need to pick node 1 at the end. So this node always gives us +1 turn. But this node only gets picked half the time. Right? Half the time we pick it first, and half the time it gets deleted along with node 1. So this node only contributes 0.5. So this node contributes 1, this node contributes 0.5, answer 1.5. Okay, let's look at C, at this case. So again, this node contributes 1. What about these nodes? Well, so what's the chance that node 2 gets deleted? Either it gets deleted on the very first turn, with 1/3, or what's the other way it could get deleted? If we pick node 1, it doesn't get deleted, but if we pick node 3, it could still get deleted. So it's actually, if we pick node 3, then we're back in case B, where it has a 1/2 chance of getting picked. So its total chance of ever getting deleted is 1/3 plus 1/6, which is 1/2. So this node gets deleted half of the time, and this node, it's symmetric with this one, so it actually also gets deleted half the time. And so according to this method, our answer should be 1 from this node, a half from this node, and a half from this node, which is 2, which is what we got. So that's looking good. Okay, so how about this case? Well, this node contributes 1. This node, well, let's see. So it has, again, a 1/3 chance plus of getting picked initially. The other way it can get picked is if we pick this guy and then this guy, which is 1/3 times a half. So again, that's a half. So this guy's going to contribute a half. And how about this guy? The only way that we get to pick this guy is if you pick him straight out. So that's a 1/3, right? If you pick either of the other two, then he gets deleted before he gets picked. So according to this node adding up thing, this guy contributes 1, this guy contributes a half, this guy contributes a 1/3. And what do you know? That adds up to 1 5/6. So this solves all our examples. That's nice. So let's see if we can actually figure out how to count the contribution of a node. So a really interesting thing is that, let's say you have a child of the root. I think I'm going to show you that no matter what else is going on, right, there could be arbitrary, other stuff, other children. This guy always contributes 1/2 if he's a child of the root. So why is that? Well, so think about how he can get picked. The only way he can't get picked is if we pick node 1 before him. It doesn't matter what happens, in all these other children. Right, they're not going to delete him. The only way that he gets deleted, right, which is the only way that we can't pick him, is if he gets deleted, A node gets picked, or it gets deleted without us picking it. The way that it gets deleted without us picking it is if we pick one of its parents or ancestors. Right, the only parent here is 1. So the only way for this guy to get deleted without getting picked is to pick node 1. Regardless of what's happening, what other moves we're making. And what is the chance that we pick 1 before 2 versus 2 before 1? Well, because on every turn, we're just picking a random node. There's no bias towards any particular node. It's always a half, right? You can think of it another way, is that every turn, one of 3 things happen, from our perspective. We either pick node 1, we pick node 2, or we do something else. And regardless of what the something else is, it doesn't affect, 1 and 2. So eventually, we're going to run out of something else, and we're going to actually do node 1 and node 2. And it's 50-50 when that happens. So the chance that this guy ever gets picked is just 50-50, no matter what. And we can actually extend that reasoning to an arbitrary node. So let's say we have some node way down here, right, and there's a bunch of other stuff happening in the rest of the tree. What is the chance, though, that this guy ever gets picked? Well, how does he fail to get picked? Is if any of these 3 get picked before him. Right? To get picked, he has to be the first one among these 4 to get picked. And what is the chance of that happening? It's just 1/4. Because regardless of what's going on in the tree, also in the tree, it's not going to affect this path. The only thing that this node cares about is the first guy in this path that gets picked, and the chance that he's the first guy is just 1 over the length of the path, 1/4. So actually, that works for every node in the tree. Every node in the tree, the only thing it cares about, there is a chance of getting picked, is whether or not it gets picked before any of its ancestors. And the chance of that is just 1 over the length of the path from it to the root, right? 1 over the number of ancestors that it has, including itself. So the answer is actually just the sum over nodes of picked, which is sum over nodes of 1 over the depth, where the depth of the root is 1, the depth of the children is 2, and so on. So yeah, that's actually all that's going on here, is instead of thinking, we want the number of turns, which is the number of nodes that get picked on average, which is just the sum, for each node of the probability that it gets picked, sort of on the average run, which we've argued is 1 over its depth. So let's code that up. So I think I'm going to need input, output, and also vectors. And my usual prefix. So we can do n, and there's n minus 1 edges. That's what it says. Yep. And they each contain just 2 nodes that are connected, and the root is always node 1. So I'm going to 0 index. I think that's usually nicer. And just keep track of, for every node, what its edges are. So it's just a general way to represent a graph. And we're going to now compute the depths. So to initialize everything, right, so initially every node had an empty set of edges, and every node, let's say, starts with depth 0. And also we're going to have a list of parents for, right, so I haven't actually said how I'm going to compute the depth of the tree. Let me do that now. So, right, so this root method is just going to sort of recursively go down the tree and assign depths and also a parent to each node. Well, actually, we can just take the parent. X equals B. And we also need to know the adjacencies. So we want to go to all of our children. That's why I need to keep track of the parent, so we don't think that our parent is actually one of our children. So we're going to recursively go down to our child. We are the parent of that child. Its depth is our depth plus 1. And we can pass through these vectors. And the answer is just a floating point number. And floats. For that too, and takes, let's see, -1 and E, and it also takes the depth, which we said we wanted to start at 1. So let's try it out. 5. And this should be 2. And we will also, let's see, this is 2. Cool. And let's try our last example, which was 1, 3, 1, 2, and 2, 3. Right, this was example D. The length 3 path. 1 point, and I believe that's 5/6. So let's give it a shot. I may not have enough precision there. Okay, looks like it might take a little while to judge that. I'm pretty sure it's right though. So yeah, this is this problem. I think it's a really, cute setup, right? It's pretty simple. Just keep deleting random nodes until you're done. It's a pretty cool problem, and it has a pretty beautiful solution, right? Instead of this recursive thing where you think about all possible trees is just impossibly slow. But if you think about it from the perspective of each node and the chance that that node contributes, right, gets picked, then you end up with really something really simple, just the sum of the reciprocals of the depths. So that's it.